In this video, we're going to talk about how to find zeros of a polynomial. In particular, we're interested in finding zeros that might be difficult to identify. So as you can see in this graphed example here at the top, we have three zeros, one right here, one right here, and one right here, and they are all not whole numbers. They're all decimals. And it might be difficult to know which decimals they are. The way we know the exact decimals are using what's called the rational root or rational roots theorem. So here's the theorem. Let's read it. And I left it exactly as it was in the book. And we're going to use an example, and that example is going to help explain it. So if we have a polynomial where the coefficients are integers, and we're trying to find a rational zero. Rational is another way of saying a fractional zero of the function. Then it's going to be in the form P over Q, where P is a factor of the last term and Q is a factor of the first coefficient. I said term, but it's first coefficient. So what we're going to be looking at is the first and last numbers in the polynomial, and what numbers they have as factors. That's going to help us figure out possible potential zeros for the polynomial. Okay, kind of rough to say, a lot easier to see. So let's do an example, and I think that'll help kind of make sense from that statement. Okay, so this is our function, and we want to use the rational roots theorem to list all possible rational zeros of this function. Okay, so first thing I'm going to do is I'm going to look at the first constant, which is 2. Oops, I selected highlighter, but of course, as always, it wasn't ready. 2, okay, and I want to list the factors of 2, things that divide into 2. So numbers that divide into 2, well, that would be 1 and itself, right? So 1 and 2. But technically, we're going to include positive and negative combinations of 1 and positive and negative combinations of 2. And you'll notice that that's actually in the theorem up here, right? They have a plus or minus because they're including possible positive negative combinations as well. Okay, so 3. And notice I'm going to ignore the fact that there is a negative on it because I'm going to include positive negative combinations, has the same factors, 1 in itself. So 1 and 3. Okay, so what we're seeing is 3 is behaving like P and 2 is Q. So according to the theorem, possible roots are the factors of P over Q. Okay, so let's list possible combinations of P over Q. So let's start with when P equals 1. Okay, so when P equals 1, it could be over the factor 1 for Q. So basically, I'm pairing up these two factors right off the bat. And then plus or minus, boop, plus or minus. Okay. Then if P is 1, it could also be paired up with the other factor for Q, which is 2. So I can pairing up those two now. And then plus or minus. All right. Another possibility for P is that we could be working with the number 3. Okay. So now we're going to pair 3 with the different factors for Q. So 3 over 1. I'm referring to the first factor again right here. And then, of course, I'll throw the plus or minus in front. Plus or minus. And then 3 over 2 would be the other option. And including the plus or minus. Okay. Now, real quick comment. We can simplify. 1 over 1 is just 1. So this is just plus or minus 1. 1 over 2 is obviously 1/2. I'll just leave that alone. 3 over 1 is 3. And then 3 over 2 is 3/2. I'll just leave that alone. And as you can see, what we have discovered now are possible rational numbers, which they called R in the theorem, that could be the zeros, and some of them are fractions. And it gives us a place to start when we're trying to figure out which numbers we're interested in as possible zeros to the functions we're looking at. Okay, so let's do this in practice now. Let's find the horizontal intercepts for this function, okay? So basically what that means is I need to figure out which of these possibilities goes into f of x. And the quickest way to do that is to use synthetic division. All right, so I'm going to start with the first number. I'm going to start with 1, and I'm going to try to divide 1 into this function using synthetic division and see if it works. Okay, so 2, 4, -1, -6, -3. Great. Okay, dropping 2. So that gives me 2, which is 6. That gives me 6 times 1 is 6. -1 plus 6 is 5. 5 times 1 is 5. Putting it in the next column, then that's -1, -1. Okay, I already know it's not going to work. That's not going to be 0, right? And in order for it to work, to be an intercept, it has to have a remainder of 0, because this last number here is the remainder. Okay, so 1 doesn't work. And here I'm going to go ahead and erase this. Now you could go ahead and work right next to it. But now we're going to try -1. All right, so still dropping 2. 2 times -1 is -2. That's going to give me a 2, -2 again. That's going to give me -3, +3 this time. That gives me -3, +3 again. Ah, there we go. Yay, we found a 0. So what we've just figured out is this thing crosses at x equals -1. So one of the horizontal intercepts is -1, 0. Okay, so I've got that one. Now, what's remaining, I'd like to find another one, and I'm going to keep dividing. So this is where we're going to kind of pause for a second. And I'm going to, in order to make my life a little bit easier, right? Because I could keep going through all of these and it could take a while. But I'm going to go ahead and cheat a little bit, as it were, and I'm going to use technology. So what I'm going to do is I'm going to hop into Desmos. All right, and let me go ahead and do that. I'm going to get my keyboard really quick for doing this. So we're going to go ahead and we're going to graph this just so we could kind of get a better idea rather than playing this game of dividing. Okay. Okay, so here we go. I'm going to enter in the function once this loads up. Okay, so f of x equals, okay, so what was it? Got to look it up again. 2x to the 4th plus 4x cubed minus x squared minus 6x minus 3. Okay, now here's what's interesting. We know -1 works, and we can kind of see that here, right? So I'm going to kind of zoom in. Oops, sorry, I tried to do it with my fingers, but it kind of like didn't like that. Kind of zoom in. But what I'm seeing is it looks like it's cubic, right? Like it's going through like a cubic. So I'm thinking that there's like a multiplicity thing at -1, meaning -1 is a root more than once, possibly 3 times. Okay, so I'm going to go back now that I know that input. I'm going to come back here and I'm going to try -1 again. And I'm going to see if -1 works. One more time. Okay, oops. I meant to do it right next to this. Oh, okay, there we go. So I'm going to divide -1 into this result. So here we go. So that's 2. Okay, 2 times -1 is -2. That's 0. That's 0. That's -3. That's +3. Yes. Okay. So it has a multiplicity, at least of 2. It kind of looked like 3, right? Kind of looked like 3. But for right now, what I'm going to do is I'm going to cheat. I'm going to stop right here. And I'm going to take this final answer right here, and I'm going to write it as a quadratic. So this would be 2x squared plus 0x minus 3, which really we would write 2x squared minus 3. And I'm going to go ahead and solve this. And this is actually pretty easy. I don't even need to use the quadratic formula. I could just set this equal to 0, add the 3 to both sides, right? And then take the square root of both sides. So that's going to give me, actually, no, wait, here. Let me divide by 2 first. Sorry. So first dividing by 2 is 3/2, and then taking the square root of both sides. Boop, boop. And that's going to give me plus or minus radical 3/2. Yuck. Okay. But what this means then is that it actually doesn't really have a multiplicity of 3 at -1. It means that these two numbers are actually more exact. We can rationalize the denominator on this, by the way. It's probably been a while since you've seen that. But let me show you what that would look like if I rationalize the denominator. That means there's, okay, denominator, there we go. That would mean that I'd break it up as 3/2. I'm going to ignore the plus or minus for a second. Radical 3 over radical 2, sorry. And then I multiply top and bottom by radical 2, which would give me the square root of 6 over square root of 4, which is 2. So as a rationalized denominator, this would also be a potential answer. So, or plus or minus radical 6/2. Okay, so here's what we got then. We have from the original that we have -1, 0 with a multiplicity of 2. And then we have radical 6/2, 0. And then negative radical 6/2, 0. Or you could do it as radical 3/2, like the original form. That's fine. But these would be the horizontal intercepts for this function. And as you could see, the picture, though it kind of helped us, wasn't perfect in us understanding where the actual horizontal intercepts were. And part of that has to do with, like, you would have to zoom in really close to get a better idea that it really wasn't a cubic, that it was probably doing something like this, like it was probably like going through the, I'm doing a terrible job because it should have been shifted over this way. Boop. Okay, do this. Boop. All right. It was probably doing something like this, and it was so small we couldn't even see it. Like it was at -1, so it probably bounced off, but it looked like it went through. But it's like you'd have to zoom in really close in order to see that. We're not going to bother with that. We're just going to go ahead and move on because we solved it. But it kind of shows you that the pictures aren't even perfect, and it helps to have these techniques for us to find the zeros, just some nice solid techniques using the technology to help us, but then using these techniques to make certain that we know exactly what the zeros are. By the way, if you did put this into the calculator, I want to say I did that. Let me see. Yes, so this is actually 1.22, just so you know. It's approximately 1.22, and then of course plus or minus 1.22. So yeah, it's just an interesting little thing that's going on there that we couldn't really see. Let's try this again. New problem, new idea. We want to look at potential zeros. So let me start with that. So let's see, P and Q. So let's see, Q. Here, actually, I'm going to start with P just because it's going to go on top. So P is referring to the last number, okay? So multiples of 2, factors of 2, I'm sorry, factors of 2. So that would be 1 in itself. And for the moment, I'm going to go ahead and drop the plus or minus because I'll put that on in a moment. Q, we're going to be looking at the first term, which is 4. Allison, just wait a sec. Okay, there we go, 4. And multiples of 4, this one's actually more exciting. I mean, factors of 4 is more exciting. It's not only just 1 in itself, but 1, 2, and 4. Ooh, so exciting. Okay, so possible factors are, for P over Q, 1 over 1. I'm going to put the plus or minus now. 1 over 1, 1 over 2, and 1 over 4. So basically I did 1, the first factor for P, with all the factors of Q, okay? And the second factor of P, which is 2, over all the factors of Q. That's what I'm going to do now. over 2 and 2 over 4. Okay, now here's an interesting thing. We actually have some repeats. So first, 1 over 1 is just a 1. So this first one just simplifies to 1. Okay. 1/2 and 1/4. Okay. Now 2 over 1 is just 2, but 2 over 2 is 1, which we already have listed. That's right here at the front. So it's already there. I don't need to list that again. Same with the last number. 2 over 4 is 1/2. And I already have that listed right here. So I don't need to list the last two. I'd be just, being redundant. Okay, so there we go. There's our possible factors. Sorry, I want to switch back to red. Our possible roots. And let's again look at the graph. Use that to help guide us as to which of these we should start with first. Now, back in the days when we weren't using the graphing calculators to help us, we would just start guessing. Like you'd literally just start guessing. And as a student, I would always start with the easy ones, right? Like I'd start with the 1 and then -1 and then 2 and then -2. And I would save the fractions until I had to use the fractions. But technology has made our life a little bit easier. So let me go ahead and bounce back over to Desmos. And let's enter. Oops. I'm just throwing things across my desk. Got attached to the magnet on this board. Sorry. Let's go ahead and enter this new function. So it is, okay. Sorry, I moved away. Let me go back. Oh, there we go. Okay, 4x cubed. X cubed minus 10x squared. And then it's minus 2x plus 2. Okay. Boom. Okay, here we go. Okay, a good candidate would be the fractions. In particular, I kind of like the left one. It looks like it's 1/2, doesn't it? -1/2. So that's what I'm going to start with. I'm going to start with -1/2. And then I'm going to try the rest. Or maybe use the quadratic formula if I can at that point. That's kind of what I go to next. Okay, so I'm going to try -1/2 and I'm going to see if it works. So that's going to be 4, -10, -2, and 2. So as you can tell, my old school technique, it would have taken me a while before I would have gotten to this one. Okay, so thankfully, multiplying by 1/2 is easier. We're just dividing by 2. So 4 times -1/2 is -2. And then those two add up to -12. Okay, so that's -12 times -1/2 is +6. And then that adds up to 4. 4 times -1/2 is -2. Yay, we got 0. Okay, cool. First one, we have found that one of the real zeros is x equals -1/2. So I'm just going to go ahead and put that up here for my answer. And I'm going to take then this remaining equation, 4x squared minus 12x plus 4, and I'm going to go ahead and solve this either using the quadratic formula or factoring. I just don't want to go through the process of finding any more. Okay, so I'm going to set it equal to 0. I'm going to factor out the greatest common factor, which is a 4. X squared minus 3x plus 1. Okay, there are two numbers that multiply to be 1, but add to be -3. That does not exist. So I'm going to have to use the quadratic formula. Okay, so x equals, and I'm using, by the way, the quadratic formula on just what's inside here. I'm going to ignore the 4. All right, there's no reason to include it in the quadratic formula. Okay, so I get x equals 3, because it's -b, plus or minus the square root of -3 squared minus 4 times 1 times 1 again, all over 2 times 1. Okay, so that's going to be 3 plus or minus the square root of, okay, so that's 9 minus 4, which is 5. I don't need a big giant square root for that. Over 2. Boom, there we go. So there's the other two zeros. X equals 3 plus radical 5 over 2, and x equals minus radical 5 over 2. Plus or minus radical 5 over 2. Now, since I don't have space, I'm going to be lazy and just write it like that. But you may have to list them separately. You may have to do 3 plus radical 5 over 2 and 3 minus radical 5 over 2. That's how we would approach these problems.